Greetings and welcome, friends. Mr. Wada here. We're talking about volumes of prisms and cylinders. The volume of a solid is the number of cubic units contained in its interior. All right, so it's the space that it takes up versus like surface area. We'll talk about later in this chapter will be like the amount of paint it would take to cover the object. All right, so this would be how much it can hold. Maybe you could think about it that way. So it's measured in cubic units such as cubic centimeters or cubentimeters. Cavalieri's principle, named after Bonaventura Cavalieri from 1598 to 1647. It's still named after him, even in 2017. States that if two solids have the same height and the same cross-sectional area at every level, so if I infinitely slice this, right, and each of those slices has the same cross-sectional area, then they have the same volume when they have the same heights. And that even works if I tilt one of these stacks, all right? So if I tilt this stack, and as long as the height between these are identical, they will have the same volume. That reminds me of triangles that have the same height and the same base, all will have the same area, even if you skew one significantly. All right, so in terms of calculating the volume of a prism, the general volume of a prism is going to be the capital B area of the base. No, it could actually, this could be 1,000 miles away. This could be 1,000 miles. And they would still have the same volumes. It does. Like a stack of note cards that's been slightly tilted. No. Yeah. Well, anyways, capital B is area of the base. So the area of the base is a capital letter because it's based on a formula. So it might be length times width. In the case of a square, it might be half the base times the height. Lowercase base, that is, if it's a triangle. You might have area of a trapezoid, like half the height times the sum of the bases. It could even be a regular polygon or the area of a sector. Right? I could take a sector and prismize it, so to speak, even though this is actually not a prism because of the curved surface. And I could then have a solid, right? And if I find the area of the base and multiply by the height, that will give me its volume. It's a solid. It's a thing. Yeah, it's a solid. It's a sectoragon. No. Here's example 1. Let's find the volume of each prism. So first of all, what is the name of this figure? It's a good guess. Anthony, what do you think the name of this solid is? Triangular prism, right? So the base is going to be the triangle. Now here we notice this is a right angle marker. So to find the area of a triangle, cap B is going to equal half the base of that triangle times the height. So half of 4 times 3 or 3 times 4. I'll put the 4 first because it's even and divisible by 2. So half of 4 is 2. 2 times 3 is 6. So there's the area of the base. So now if I want to multiply that by the height, that will now give me the volume. All right. And so I'm going to take the area of the base and multiply by the height. Notice these are in the same units. And so I'm going to get the volume is equal to 12 centimeters cubed. Cubentimeters. Right? Right? So there we go. There we go. Now, if I asked a question about surface area, you would have had to find the hypotenuse of this triangular base as being 5 and then find the area of all of those, but we'll talk about surface area later. Let's see, how about, nope, not here. Malik, what is the name of this wonderful polyhedron? Trapezoidal prism, I like it, because it has two bases that are trapezoids. The area of a trapezoid formula I mentioned up here a moment ago, half the height times the sum of the bases. You also could have imagined that as being the average of the bases times the height. So it looks like if this is 6 centimeters, right, 6 centimeters, 14 centimeters is that other base. So I'm going to have the area of the cap B base, right? Capital letters are reserved for variables that are kind of like compound. They are like built from formulas of other linear dimensions. Is I guess the way I might describe that. So the area of that trapezoid is going to be half the height, which is 3 centimeters, times the sum of the bases. So that's 14 plus 6. So that's half of 3 times 20. Half of 20, I'll divide the even number by 2, is 10. Times 3 is 30. So there's my base, and if I now multiply that by the height of the prism, that will give me my volume. So I'm going to have 30 times 5, and I'll get volume is going to be 600 centimeters cubed. Yeah? We liking it? I like it a lot. Because we'll consider what I've multiplied in here. The units for this 3 was centimeters. The units for this sum was centimeters. So centimeters times centimeters is centimeters squared. And then if I take centimeters squared and multiply by 5, which was in centimeters, that would be centimeters cubed. That's a good question. Yeah. Yeah, so cubic centimeters is literally asking how many 1 by 1 by 1 centimeter cubes would fill this space, is kind of what it's asking, right? So it's asking, right, if I had a lot of tiny little cubes, how many could fit inside that trapezoidal prism box? And obviously, with the corners being funny, I'd have to like slice them off and rearrange them and try to get it to fit correctly. It turns out the volume of a cylinder, even though it's not a polyhedron, is very much the same idea. It's just going to be the area of the base multiplied by the height. And in this case, the area of the base is a circle, so it's represented by pi r squared. Right? Right? Not bad at all. And I'm assuming you guys have seen volume formulas before. Yeah? You see this in like middle school or something? No? I'm getting no response. Yes! All right, let's find the volume of these cylinders. So here's the, let's find the area of this circular base. So cap B, I'll call it, is going to be pi times, that 9 is a radius, so that's exactly what I need. 9 squared, so that base is going to be 81 pi. And the volume, I'll then multiply that base times the height. That's going to give me the volume, the V. So I'll have 81 pi multiplied by 6. These are all in feet, fortunately. And 6 times 81, 6 times 8, 486 pi, is that right? I'm not getting a no. And that would be cubic feet. So there would be the answer there. If you wanted a decimale approximation, we could calculate what 486 times pi is. And so that is 1,526.81 feet, feet cubed. All right. They calculate river flow in cubic feet per second, CFS. So if you ever go on the internet and you want to figure out what is the flow of the Connecticut River near us in Brattleboro, I forget where the closest dam site is where they track that, but it might be up near Bellows Falls or in Greenfield. But you can actually calculate the number of cubic feet per second that are passing by any point in that river, and then figure out how much volume of water is moving through there. And a cubic foot, I've been told, is roughly the size of a basketball. And so when I would paddle the Millers River in Athol, Massachusetts, or from South Royalston to Athol, and it would be like 1,200 cubic feet per second for the volume, for the flow of that river. That would be like if every second 1,200 basketballs were passing by me as I look out towards the river, right? Well, it depends on how wide the river is as well, right? So like if it's a really wide river, that's super easy. But the narrower it is, that's the faster that it's moving. And so if you know kind of the river, if you're familiar with the river, you could talk about its volume flow in cubic feet per second. Let's see, here we go. So here's another cylinder. So yeah, you guys get the idea. The area of the base is just going to be pi times 4 squared. So that's 16 pi. And then the volume is going to be that 16 pi multiplied by the height. Wait a minute, does this matter that it's crooked? No. This is a height, right? The only thing to be aware of is what if they accidentally gave you this, which I would refer to as like a slant height? Then you might have to do like a Pythagorean theorem to find the actual height. So make sure they don't try to trick you or nothing. Let's see, 42 plus 70... 112 pi centimeters cubed. Right, so there you go. Cubic feet per second, man. I used to be able to know my rivers so well that when we'd get like a good rainstorm, I'd be able to be like, tomorrow afternoon at 2 p.m., it'll be at its maximum cubic feet per second. It was excellent. Yeah, I would be able to like make sure like I'd time it with when I'd go out and be able to figure that out. So let's see, here's density. I think you've done this maybe in a science or a physics class or a chemistry class even. You've probably even done it in terms of moles. What's that, 6.28 times 10 to the 23rd or something like that is a mole? I don't remember. A mole, M-O-L-E? No, maybe you'll find out in chemistry someday. Density is the amount of matter in an object, is the amount of matter that an object has in a given unit of volume. All right, the density of an object is calculated by dividing its mass by its volume. All right, different materials have different densities, so density can be used to distinguish between materials that look similar. For instance, table salt and sugar look alike. However, salt has a density of 2.16 grams per cubic centimeter, while sugar has a density of 1.58 grams per cubic centimeter. So if you're buying a pound of sugar versus a pound of salt, one of those containers must have less volume. Or if you buy from two containers that have the same volume, they would have, right, one of them, the salt, would be much heavier, assuming its capacity is filled. So let's see, using this density formula, but don't you wish it was butter, though? Whoa, there we go. My mouse had died for a minute there. Destiny. The diagram shows the dimensions of a standard gold bar at Fort Knox. Gold has a density of 19.3 grams per cubic centimeter. Gold is AU, right, on the periodic table of elements? Yes, maybe? Mm-hmm. Yeah, someone, yeah. Mm-hmm. Wow. So 19.3 grams per cubic centimeter. Find the mass of a standard gold bar to the nearest gram. All right, so if I know the density and I'm looking for the mass and I know the volume, I'm going to end up solving this equation for m by multiplying both sides by v. So let's plug in what I know. So right now I know the density is 19.3 grams per... Oh, what? No, they didn't. Blast. Guys, look at that. This is per cubic centimeter. These are in inches. So let's convert these to centimeters. Little known fact, 1 inch is equal to 2.54 centimeters. Okay? So I'm going to multiply each of these by 2.54. I get 17.78. All right, and I recommend converting these before I calculate volume. This is going to be 9.2075 centimeters. And 1.75 times 2.54, I'm going to get 4.445 centimeters. So the volume is just going to be the product of those 3 centimeter numbers. So 17.78 times 9.2075 times 4.445. Centimeter times centimeter times centimeter is going to be centimeters cubed. And if I multiply all of those out, I find that it is 727.69 centimeters. Did a little bit cheating off the book there real quick. There you go. That's what you get. So if this is the volume, I'm going to plug this in here. And how could I solve for M? Multiply both sides by 727.69, and that should give me the mass of a gold bar. All right, so let's multiply those. And I get 1,444 grams. So yeah, let's find out how many pound. Let's see, 14044 grams in pounds, lbs. That's equal to 30.96 pounds. So every gold bar is 31 pounds, and they sell gold by the ounce, right? Which is what is an ounce is a 16th of a pound. I don't know. No one's gonna correct me, but the internet can later. So the internet can. So, let's see. All right. So these volume formulas, you can also plug in what you know and solve for what you don't. What if the volume was given to me, but I didn't know one of the dimensions? Right? I can write a formula. So this is looks like, what type of solid is this? What's the name of this box? What's it called? Rectangular prism. So that's going to be the length times width times height will be the volume. So let's plug in what I know and solve for what I don't. So I know the volume is 72 here. The length we'll call 6. The width we'll call 4. And the height is unknown to us. I'm going to get 72 is equal to 24h. And then what do I do to solve for h? Yeah, plug in what I know, solve for what I don't. So h is going to equal 3. And what's that going to be measured in? 3 feet. So the volume was in cubic feet, and therefore these linear dimensions are all in feet. Like a tall coffin. All right, last concept here that I'm going to get to today. Similar solids. All right, 2 solids of the same type. We did similar areas back in the day. Do you guys remember that? Right, if I have right two shapes, that would say this was like a 1 to 3 for the linear dimensions. What did we find out about their areas with respect to each other? All right, linearly it was times 3. And then do you guys remember how the area is related? Yeah, it was times 3 squared, right? So that would be 9 times as much area. But now suddenly if I made these into volumes, that the volumes are going to be multiplied by 3 cubed. And so this would actually have a volume that is 27 times greater. I'm saying linear dimensions might have a scale factor of like 1 to 3. So area, square units, if I'm comparing the areas where the scale factor was 1 to 3, this is going to be 1 to 3 squared. So it's 9 times as much, and volume will be cubed. So depends on if you're converting linear, area, or volume of similar solids. It's going to be the scale factor cubed is what you end up having. So that's kind of an interesting thing. We'll actually talk about that in a video in a couple days about what is the largest organism. And it's a surface area volume problem, actually. So check this out. These cylinders are similar, they're telling me. Okay? So that means because they're similar, I would expect that the dimensions are all scaled up by a scale factor. What is the scale factor K here? 6 divided by 3, which is 2. And if I know the volume of this one, and I want to convert to the volume of that one, I expect volume of cylinder B is going to be 2 cubed times 45 pi. All right? Volume is cubic units, and you cube the scale factor. All right, so that's going to be 8 times 45. I feel like 8 times 45 is something I definitely should know, but I don't. 360. 360? Oh my goodness, Mr. Waddy. Shame on you. It is, absolutely. So 360 pi cubic, I'll just call it, yeah, centimeters cubed, will be the volume of that cylinder. All right, let's see. And I think that's where I'll leave it for today. Thanks for watching, Internet friends. Bye-bye.